Okay, ready to go? So today we're starting a new phase, so to speak, and it's the biggest chunk of the material during this quarter. So we started, or I started, by going over some concepts, situating spatial analysis and spatial data science, and then we moved on to visual analytics and how you can use graphical devices and maps and interact with them to discover patterns and create hypotheses. Now we get a little more formal, and now we move to the topic of spatial autocorrelation. And today I'll just kind of set the stage, talk about the null and the alternative hypotheses, and then also spend quite some time, and in the lab we'll do as well, on the concept of spatial weights, which are kind of a tool to get everything to work. And then we'll move on to actual statistics for spatial autocorrelation, so global autocorrelation statistics. We will go both look at the data from a lattice data perspective. If you remember the first class, lattice data are discrete data, and then we'll also look at continuous surfaces from a geostatistical perspective. That's another way of thinking about spatial autocorrelation. And then we move to local spatial autocorrelation, which is cluster detection, statistical cluster detection. So that's kind of four major pieces, all related to the concept of spatial autocorrelation. So as I mentioned, what I'm going to do today is talk about spatial randomness first. Then that's the null hypothesis. I'm assuming all of you are familiar with that terminology. The alternative hypothesis, so once you reject the null hypothesis, what do? Is either positive or negative spatial autocorrelation. And then I'll get a little more technical, also a little more mathematical, and talk about what is actually a statistic to test for spatial autocorrelation. How do you think about that? How do you construct that? Without going into specific test statistics yet, but just kind of the concept and formally, and then we'll see a big part of that is the spatial weights, which we'll then spend some time on. So in terms of readings, chapters 3 and 4 in my Modern Spatial Econometrics book basically describe everything I'm going to talk about. I have given you some additional stuff, in particular for those of you interested in working in R. There's a manual for the package SPDEP that deals with spatial autocorrelation and spatial regression. There's a vignette in R. Vignettes are little mini manuals on how to create spatial weights. It's English spelling for neighbors. And then if you want to get technical, the Bivand and Al book in chapter 9 talks about it. My general recommendation in practice is create your weights in GeoDa. Even if you're going to do analysis in R, it's orders of magnitude faster, and they all read the same files. So you make them in GeoDa, then if you want to do the analysis in R, you read them into R, and you move on. We'll see that later on. Okay, first, spatial randomness. What is spatial randomness? As I mentioned, it is the null hypothesis. It is the frame of reference. And it's really not a very interesting frame of reference. Randomness is when you don't have any pattern. There's no rhyme or reason to it. That is truly random, is actually what the colloquial term random means. You can't make any sense out of it. It's totally random. So spatial randomness is actually not interesting, but it's very important because it is the beacon, it's the reference frame against which we compare everything. So really, our mission in life, so to speak, is to reject spatial randomness, which means that there is some structure in the data, and then we want to discover that structure and later on explain that structure. So that's what it's all about. So we want to reject the null. So what does this null really mean? It means that if you think of the great data generator out there somewhere that puts values in space, it means that any pattern that you see is equally likely as any other pattern that may have occurred. So in other words, there's no rhyme or reason to it. There's no structure to it. The value observing something at one location doesn't tell you anything about what might be at the other locations. Okay. That's truly random. We've actually already seen this. In the first lecture, I showed you the true map of Milwaukee and then a random map, and I'll show it again in a few minutes. So under spatial randomness, operationally, it doesn't matter where the values are. If you remember the Milwaukee example, there was a histogram for the true map and a histogram for the fake map. They're exactly the same because the distribution of the actual values is the same. It is where they land that matters. If where they land does not matter, we have spatial randomness. If it does matter, we don't have spatial randomness. So in other words, we can fake it. And this will be very important. Later on, we'll see this again and again as a way to do statistical inference. One of the
to define this formally, would we just say that like latitude and longitude are orthogonal to anything we're interested in?
what you would say is that the coordinates in space are a uniformly distributed random variable. So they could be anywhere, right? And this is actually how you, say, mimic a random point pattern. You create uniform between 0 and 1. Say if you put them on a unit square, you take uniform random numbers, and that's a random pattern of points. In our case, there's two aspects to it because the frame is fixed. It's the location of the values in the frame that is random. Okay? So if you have a list of locations with lat and long, and you have a list of your values, you can just put them wherever. Just throw them in there. Right? So there's two things to spatial randomness. One has to do with the location, which I think is where you're getting at. The other has to do with the allocation of the values to the location. That's the random part we're focusing on here. In a few weeks, we'll focus on the other one as well. Okay? So
can there be randomness that is coordinate? Can there be coordinate systems that don't have randomness where others do?
Yeah.
Like you have singularities and stuff?
no, not coordinate systems. Points. Right? The coordinate system is neutral. It's the location of the points that can be spatially random or spatially structured. And spatially random has a very formal definition. We'll talk about that in a few weeks when we deal with the point patterns. But this is different. Remember the first lecture when I made the classification of the different types of analyses. In some analyses, the location is given. In other analyses, the location is itself random, right? This discussion is for locations that are given. The location is given, but the distribution of the values of your variable of interest over these locations is actually random, right? So there's no such thing as a highly segregated city. Everybody's located randomly in the city, right? So, which gives us a handle to actually mimic spatial randomness. Because one of the, as I was starting to say, one of the downsides or interesting parts to spatial statistics and spatial analysis is that the math is very complicated. And it's very difficult to analytically derive, for example, for a test statistic, what its distribution might be under a null hypothesis of spatial randomness. It's very difficult to do. But what is easy to do is to computationally mimic it. Because, and we'll be doing this over and over. Basically, what we're going to do is mimic spatial randomness by taking our distribution of the values and randomly putting it on our locations. Compute a statistic. Do it again. Compute a statistic. Do this many times. This gives us a reference distribution for the statistic that mimics spatial randomness. And we'll come back to this concept later. Yes. Well, there's several technical issues related, but basically it's a random reshuffling of the technically it's a pointer, but let's call it an identification value for each location. So let's say value 1 has tag 1, value 2 has tag 2, and so on, and say that you have 50 of them. You take the list 1 through 50 and randomly reshuffle it, which then, you know, puts your first value maybe on location 5, and your second, and then you reshuffle it again. So you actually don't move the data to the location. You shuffle the identifier, you know, over the values. Yeah. Okay. So you've seen this map before. I hope by now you know which is the real Milwaukee and which is the fake Milwaukee. The structure that we're interested in is something that makes sense. And here it's very important to think of what is called Tobler's first law of geography. Everything depends on everything else, but closer things more so. So what is important in this is that there is a distance decay. In other words, if you move far enough away, there is no more correlation. There is a structure to the correlation that's related to a distance decay effect. So closer locations are more correlated. Further apart locations are less correlated. If you move far enough, they're not correlated. Right? So the importance of distance decay, we'll see that over and over again. So this is the setup. This is the null hypothesis, if you wish. And then the question is, what is the alternative hypothesis, right? So we actually have two. One is intuitive, the other one is not. It maybe becomes intuitive after you think about it for a while, but it's not directly intuitive. So you reject spatial randomness, which means you lean towards discovering structure. One type of structure is when you have like values in neighboring locations more often than you would expect under spatial randomness. In standard terminology, we call this clusters or clustering. That's positive spatial autocorrelation. And I'll say this a number of times, clustering of similar values, not necessarily high or low. We tend to interpret it as high or low, but that's not included. It's just similar. So positive spatial autocorrelation is what we think about when we think about clustering, about similarity, having similar values in similar locations. So you see the two components, and we'll make those more formal later on. There's a component about the similarity of the values, of the attributes, and there's a component about the similarity of the locations. And the two together bring us positive spatial autocorrelation. The opposite, if you can think of it that way, is that there are more dissimilar values in the neighboring locations. So think of a checkerboard pattern where you have, you know, black, white, black, white, black, white. So every neighbor is different from a given location. That's the extreme negative spatial autocorrelation. That's not really a notion of clustering. It's, in a sense, the opposite of clustering. And one could argue that negative spatial autocorrelation really has more to do with heterogeneity, with variability, than it has to do with similarity or dependence. But it is the statistic with the opposite sign of positive spatial autocorrelation. So one thing I'd like to point out, and this is, again, not necessarily intuitive, is that unlike in time series or in regular multivariate statistics where you have a correlation, positive means one thing, negative means the opposite. In this context, the opposite is not really quite what you might think. You know, it's not negative clustering, but it's really more variability than you would have in a random system. Okay. Clustering is less variability than you would have in a random system because things are more alike in groups, right? Negative autocorrelation is they're more different than they would be under spatial randomness. Now, one of the problems and one of the reasons why people like me are in business, is that this is very difficult to tell by just looking at it. We just went through all the visual analytics. Now I'm kind of undermining the whole rationale for visual analytics, and in a few minutes you'll see why. So positive, just to recap, positive spatial autocorrelation is clumps of like values clustering, but the values can be either high or low. If they're high, they're typically referred to as hot spots, and when they're low, they're referred to as cold spots. Last bullet, very important, difficult to rely on human perception. And if we had all the time in the world, we could run a little experiment where I can put a bunch of these in front of you, and you have to vote whether they're spatially random or not, and then when they're not, whether they're positive or negatively correlated. It's very hard to do. And as you'll see, at least in my view and in my experience, it's a little easier to do for positive than for negative. You'll see in a second why. Our brains are wired to see patterns. We see patterns even when there are no patterns. So the whole point of tests for spatial autocorrelation is to quantify this, is to say how likely is it that this pattern on the top here, which is I made it to be positively spatially autocorrelated, how likely is such a pattern to occur in a spatially random world? Okay. And if that, and we'll formalize that, you're all familiar with the notion of a p-value. If the p-value is small enough, then we'll say this is highly unlikely to have come from a spatially random system, so we reject the null hypothesis, right? The question is, it all depends on your p-value. There's always going to be clustered patterns, even in a spatially random system. They just won't happen very often. And so if you're willing to take the risk of being wrong, that's why it's called a type 1 error, you're willing to take that risk. When it's 1 out of a million, you say, well, 1 out of a million never happens. Well, that's not true. It happens 1 out of a million, right? So it can happen, but it's unlikely. So that's what this testing for spatial autocorrelation will be about, is how do we quantify this? How do we formalize that, right? So the way I generated this is I have basically an equation that has positive spatial autocorrelation built in, and I create predicted values, which generates my pattern, and I can crank up the degree of spatial autocorrelation, and as it becomes stronger, you start, quote unquote, seeing the clusters. As it's weaker, it becomes harder and harder to distinguish it from a spatially random field. Okay, that's positive spatial autocorrelation. Negative spatial autocorrelation, as I mentioned, is the opposite, right? So checkerboard pattern, and in my view, very hard to distinguish from negative spatial autocorrelation. So if we do the same thing again, the top panel was simulated to have strong negative spatial autocorrelation, and you can sort of, quote unquote, see the checkerboard pattern. The one on the bottom is spatially random, even though, at least when I first looked at it, I could also see a checkerboard pattern. But, you know, it's really hard to distinguish. And keep in mind, the way I did this is the coefficient that I used in my model to simulate the negative spatial autocorrelation is minus 0.9. That is very, very high. So it's really extreme. And even though that's extreme, it looks very similar to this one at the bottom, which is spatially random. So that is why we need test statistics for spatial autocorrelation. We cannot trust our visual impressions.
It's something not very directly related, but you could, if you join some of these like the squares together in the negative one, you could end up having a positive one on the join, right?
Yes, right. It's a scale problem. Yeah, actually both ways. You know, the measurement of autocorrelation, spatial autocorrelation, is directly related to scale. And if you remember one of the pitfalls that I mentioned in the first lecture was called MAUP, modifiable areal unit problem. And the classic study, and I may have mentioned this already, was a study of voting patterns in Iowa, where spatial autocorrelation was measured beginning at the ward level and then going up counties and higher, and it actually switches signs. You know. So it is scale dependent, and this is one of the issues that is very difficult to deal with in practice. You know, if you only have one scale, well, you only have one scale, that's it, right? But this day and age, oftentimes we have microdata, you know, like Twitter, geolocated Twitter messages, right? And we can aggregate them any way we want. And so then at which level do we do this analysis, and at which level is the measure of spatial autocorrelation actually meaningful and not indicative of, say, a problem with scale selection? I give this example a lot. I may have given it to you already, but in some work that I did looking at house prices, did I tell you this already? I know I give this example all the time, so I may have given it to you already, but it was a study of house prices, and this is called a hedonic model. So it's the price of the house as a function of the house characteristics. And we found a spatial autocorrelation that I had never seen before, you know, like 0.95. This is just hugely clustered, right? But it was in Los Angeles. And if you know anything about development patterns in the southwest of the US, this is not like here where they build one building and then maybe another one. The developer goes in and builds 3,000 houses. And they're all the same. Garage on the left, garage on the right. But otherwise, they're the same. So if you do a hedonic analysis, what this autocorrelation tells you is that there is no variability in your sample at that scale, right? We're back to our scale problem. At the individual house scale, since these houses are all 99% identical, there is not enough variability on the right-hand side of the equation. There's not enough variation. So positive spatial autocorrelation, another way of thinking about this, is as a loss of information. You don't have as much information as if the pieces that you observed were independent or uncorrelated. And so again, this is a situation where it may point to a scale problem. If you would analyze this at the neighborhood level, you wouldn't lose much information because everything within is basically identical. So these are the kinds of things you run into in practice. Okay, how do we formalize this? Yeah. Yeah, the auto part is correlated with yourself. So it's one. So it's one variable. It's not cross correlation. So the typical correlation is at least bivariate, right? You have one variable, you know, house price and income, right? This is correlation of the same variable with itself, and it's with itself in space, right? So we're looking at crime rates by neighborhood. How are the crime rates in a neighborhood correlated with the neighboring crime rates? That's the way it comes. And it's auto actually in more than one way. The big difference between time series and spatial data is that in time series, you can think of the past determining the future. It's kind of a one-directional thing. In space, it goes both ways. You know, I am my neighbor's neighbor. If I influence my neighbor influences me, I influence myself. This endogeneity, in technical economic terms, is very different from what you have in time series. And so that's why spatial regression is its whole separate field, but that's not part of this course. Okay, so maybe most of you know this. A statistic is really just something that you calculate from the data. Yeah, it's like the average or the largest number or the smallest number. You get it from the data. And a test statistic is one of these things that you calculate from the data, but it actually helps you assessing whether or not the null hypothesis is correct, and whether you can reject a null hypothesis. So let's say, if we're interested in spatial autocorrelation, the maximum value of a distribution is not going to help us very much, right? But that is a statistic, but it's not a good statistic to measure spatial autocorrelation. So we have two things to do. One is to figure out what is a good statistic, what is a good summary of the data that we can actually use to assess whether this null hypothesis holds or not, right? And then the second aspect of this is how can we tell? So one thing is how can we construct a statistic, and then the second aspect is how can we tell, given a value for the statistic, whether or not it is compatible with the null hypothesis, and in our case of spatial randomness. So we have to figure out formally the distribution of the test statistic under the null hypothesis. So assuming no spatial autocorrelation, assuming spatial randomness, what are the likely values of the statistic? And then, of course, the way we do statistical decision making is if the value that we compute from our data is highly unlikely, then we reject a null hypothesis. But the only way we can tell is if we know how that statistic behaves, in a sense, under the null hypothesis. Right? So this is just an artificial example. It's actually taken from a joint count statistic, which is one of the spatial autocorrelation statistics. So under the null hypothesis, we have the red curve, right? That's just bell-shaped curve. The statistics that we compute from the data is this blue bar that goes up. So our decision problem is this blue bar unlikely to come from the red distribution, or does it follow the red distribution? And this is where your p-value comes in. Your p-value is really the risk you're willing to take to be here, right, in this tail part. And of course, that is a decision problem. Is your p-value 0.01, 0.05, 0.10? That's up to you, really, in the end, because it is the risk you're willing to take to be wrong, right? So, but in order to be able to make that decision, you have to have the red curve. And the red curve is the distribution of your test statistic under the null hypothesis, right? So how we're going to get that? Either analytically, if we're lucky, making a lot of assumptions and then working out the math, or computationally. As I just mentioned, we're going to reshuffle the data and compute the statistic many, many times. That will give us an empirical distribution. It's not a theoretical distribution. It's based on the data. It's an empirical distribution, but it will help us make a decision and compute what we'll call later a pseudo p-value. So it looks like a p-value, it walks like a p-value, but it isn't really a true p-value. And we'll see later what is the difference. So our spatial autocorrelation statistic is something that has to capture two things at the same time. As I already mentioned, it has to get this notion of attribute similarity. That is the traditional notion of a correlation, right? Why do you compute a Pearson correlation between two variables? To see the extent to which they are linearly related, right? If they're nonlinearly related or related in a nonlinear fashion, you're in trouble. Your correlation will not be meaningful. So everything is put in a specific context, right? So what we need to do here is get that specific context to define what we mean formally by attribute similarity, right? But that's not enough, because the other part is locational similarity. So in other words, how do we formally define whether two observations are neighbors, are quote-unquote close? How do we define that, right? Do we use a geographic criterion? Do we use a social network criterion? Do we use some other kind of metric to define whether they're close? So The spatial autocorrelation statistic then will combine these two aspects. It will combine a measure of attribute similarity with a measure of locational similarity. Okay? Attribute similarity, that's the aspect that we're probably most familiar with, right? How do you capture the similarity of not two variables now, but a variable at a given location and then the same variable, hence the auto, at neighboring locations? How do we capture that, right? And so we need a variable, obviously. We have different locations. So how do we construct this function that combines the attributes at the two locations, I and j, right? And there's a number of ways. Actually, there are many different ways of doing this, and you may be familiar with them. The most commonly used similarity measure is a cross product. So it's just the product of the value observed at the two locations. And why do we use this cross product? For the same reason that we use it in a Pearson correlation coefficient, is that if there is random matching, just think of the traditional Pearson setup. You have two variables. If there's random matching of the highs and the lows for the two variables, your product will behave in a certain way. But if there's systematic matching of the large values together and of the small values together, you get extremes for your product. And so that's why it is used in a lot of measures as a measure of similarity. You just simply multiply them together, right? Now, the together is the same variable, but at two locations. Location I is our reference location. J is a neighbor, or as we'll see later, all the neighbors, right? So when there's systematic matching, so to speak, then this product will behave differently than under randomness. And that's why we like it as a measure of attribute similarity. Now, the next two are the other side of the coin. So attribute similarity, the larger the product, the more similar they are, right? Attribute dissimilarity is the other way around. The smaller the value, the more similar they are, because it measures the difference between them. So if the differences are small, they are similar. If the differences are large, they are dissimilar. They are not similar, right? And the two measures used most often in this context are square differences and absolute differences. Square differences amplify larger values because everything is squared. So it really, in the end, depends what you're interested in, whether there's not one better than the other. They just measure something different. So they both measure the difference between the same variable at two locations. One takes the absolute value, so it doesn't matter which one is larger or smaller. The other one squares it, and again, it doesn't matter which one is smaller or larger, but it amplifies the difference by squaring it. So again, same logic. Under randomness, random matching, there will not be systematically large or small values, but if all the large similar values are together, you will have very small square differences, and the other way around. If the dissimilar ones are together, you will have very large square differences. So that's the first part. The second part is this locational similarity. So we have our attribute similarity, now the locational similarity. And that requires us to formalize the notion of neighbors. And this is very tricky, and it's unfortunate, and to a lot of people it's a source of confusion or contention. And it's a necessary fact of life because, as we'll see in a few minutes, we're dealing with interaction, and interaction is two-way. You think of it as a square, but we only have observations on one of the dimensions on the square. So interaction is between all the i's and all the j's. So, you know, it's if you have, and the example I'll use in a second is North Carolina has 100 counties. So you have 100 by 100 interaction matrix. That's 10,000 cells. But we're dealing with cross-sectional data, so we only have 100 observations. How can we somehow measure interaction, measure spatial correlation from this cross-section? You know, obviously, as such, it doesn't work. We have to impose structure. We have to simplify the problem. But that's where the spatial weights come in. So the spatial weights are, you can think of them almost like an a priori. When you think that two locations should interact, or you can think of it from the other approach, are two locations unlikely to interact? And we already know that because we have Tobler's law. We know that if they're far enough apart, they are unlikely to interact. So then we shouldn't include them if we're looking for the effect of the neighbors on a particular location. Of course, the million-dollar question is, what is far enough, right? How do we define that cutoff point, right? And that's some of the stuff we'll be looking into. Important to keep in mind that the notion of neighbors is not necessarily a geographical notion, but it can also be based on, say, social network patterns. So social networks, you have actors positioned in a kind of an abstract space, and they have connections to other actors, but not necessarily to everybody else. So again, there's this structuring where you put zeros on the system. And that's how we get to a manageable system. We have this full matrix of interactions, and we start to put in zeros in different cells, so it simplifies itself. So then finally, the general form of any spatial autocorrelation statistic, and there are many, are typically a double sum, a sum over all the pairs. And you know, when you sum over all the pairs, there's some double counting because you take I, j, and then j and I. So oftentimes you'll see that these statistics are divided by 2. That's why, because you count everything twice. Of a product of this attribute similarity measure, which is going to be cross product, square difference, absolute difference, cosine. You know, there's all these other ways of measuring similarity between attributes that you can apply to the first function. And then our spatial weights matrix with the element connecting I to j, or more importantly, not connecting I to j. When I and j are not connected, that weights element is 0. And we love 0. 0 simplifies our world, as we'll see shortly. Right? Okay. So what are these spatial weights? So we get the concept, the null hypothesis, the frame of reference is spatial randomness. We don't like spatial randomness because we can't explain anything. We want to reject spatial randomness in favor of a clustering type structure, which is positive spatial autocorrelation, or in favor of a more highly variable structure, which is the checkerboard negative spatial autocorrelation. And the way we're going to do that is we have our data, and we know where our data are on the map. Very important. We have the location of the data. And so we'll construct something that measures the attribute similarity, and we'll combine that with something that measures the locational similarity. And so that is the spatial weights. Why? As I already alluded to, this is a problem that doesn't have a solution. Right? So we're trying to model, strictly speaking, n by, it's not n squared, but it's n times n minus 1 over 2, because you know it's symmetric. The diagonal is going to be 0. There's no self-similarity. I'll get to that in a few minutes. But spatial autocorrelation is about interaction. Spatial dependence is about interaction. If there's no interaction, there's no point. I have this problem often, and you might have this problem, when I ask people to come up with a data set to use in their project. I just had a case this morning in another class. Student had this really cool data set of farms in Brazil, And he had all this incredible information on the farms in Brazil. And he said, yeah, I know where they are. I have their location. But it's not a spatially representative sample. So there is no way you can deal with spatial interaction if they don't interact, if they're too far from each other. And a lot of these, stratified samples are set up to avoid that there is interaction between the farms. So there's no way you can measure spatial autocorrelation if your sample is designed to not have any spatial autocorrelation. So this is a problem when analyzing survey data that is not stratified with space in mind. Okay, so if there's no interaction, you cannot study spatial autocorrelation. So we need to get at the interaction. If there is interaction, there's too much, because the interaction is of a dimension of an order of n squared, the square of the observations, and your observations are of the order of n the number of observations. So the usual trick in statistics and econometrics is to go to the limit, is to go to the asymptote, it's called. It's asymptotic reasoning. And what that boils down to is making n very large. But you can't win this game, because as n becomes larger, n squared becomes even larger, right? So you don't gain by having a larger data set. In fact, it gets worse, right? So that doesn't work. So what do we have to do? As I mentioned before, we have to simplify the problem, right? And we simplify the problem by imposing structure and by limiting the number of parameters, by limiting the interaction. Technically, this problem is called the incidental parameter problem. It's whenever your number of parameters grows with the sample size. So if you think of spatial interaction as your n squared parameters that you're trying to estimate, the interaction parameter, as the sample size grows, there's more of those you need to estimate. So you can't win this. And for spatial interaction, the problem is even worse because it's n squared. Another instance where those of you who've taken econometrics or multivariate regression, you may be familiar with the concept of heteroskedasticity, my favorite word. It's where the variance of the error term is not constant. In other words, each observation has its own variance. How in the world are you going to estimate these variances if each observation has its own variance? Again, it's an incidental parameter problem. You don't gain by getting more observations. You only have more variances to estimate. Okay, it's the same nature of the problem. So how do we solve that problem? By structuring it, by making it simpler. So the spatial weights are designed to constrain the interaction, constrain the number of neighbors. And there's two kinds of constraints, really. One is to constrain the number of neighbors, a lot of zeros. We put in zeros in the matrix. And then the other simplification is only one parameter. So you simplify, and it's a strong simplification. You simplify the interaction. Think of it as a square, interaction from every I to every j. You simplify it by having this matrix with a lot of zeros that says only a few of these neighbors or pairs actually interact. But then on top of that, you only have one parameter. So it's the same for everybody. That's a very strong simplification. But it's a way that we can handle it, right? The other thing to keep in mind is that we have what is called an identification problem. Again, if you've had econometrics or statistics, whenever you have a model, say, where you have let's call them two parameters, A and B, and A and B are multiplied in the model. So you have A times B times some data, right? Then as A gets larger, B can get smaller, and the product is the same. So you can identify the product, but you cannot identify A and B separately because you only see them in multiplicative form. So this is a little bit of the same thing. We're trying to measure spatial interaction, and so we have our weights matrix, and we have our coefficient, but really interaction is the product of the two. So if we're going to put large numbers in our weights matrix, we'll have small numbers for our coefficient, and vice versa. If we put small numbers in the weights matrix, we'll have large numbers for the coefficient. Now, this is more important in a regression and a modeling context, but it also matters here. So one thing that we'll see, which is later, not today, next few weeks, which is very strange to people coming from time series or even from standard Pearson correlation coefficients, is that in spatial autocorrelation, for example, a Moran-Xi coefficient of 0.7 in one case and 0.6 in another case does not necessarily mean that the 0.7 case is more spatially correlated than the 0.6 case. Of course, you know, this goes against all your intuition, right? Larger numbers should be stronger correlation. But it's not, because it's the two that matter. You always have to have the two pieces together. You can only say that 0.7 is larger than 0.6 if you have the other piece. And what is the other piece? It's a weights matrix. So if 0.7 is with a weights matrix that has very different values than the weights matrix you used with the 0.6 case, they're not comparable. It's the same thing as the identification problem. The product is comparable, so to speak, but the individual parts are not, right? So always keep that in mind when you look at an analysis, and it can be really confusing if you start looking at this literature in the beginning. The actual magnitude of some of these spatial coefficients or some of these spatial statistics is irrelevant. It's their statistical significance that matters. So as we'll see later, instead of using Moran-Xi as such as a statistic for spatial autocorrelation, we will focus on the z value associated with that. The z value which we compute as a standardized value from the statistic and its properties. And since it's standardized, that's the whole notion of standardizing, we can actually compare them. Because the standardization takes into account the difference, any differences in the weights matrix. So what is the spatial weight matrix? Well, let's take an example. These are 6 areas labeled, 1 to 6. We can say, okay, the neighbors are those units that share a common border, right? That's straightforward enough. Everybody can see the common border. We'll see in a few minutes that it's actually not that straightforward. You can also think of this a little more abstractly, the neighborhood structure as a network. And a network where each of these polygons, 1 through 6, is a node, and whether or not they have a neighbor, whether or not they share a common border, is a link between them. So the neighbor structure of this layout can be represented by this simple network, where the nodes are the observations and the lines connecting them mean that there is a common border between them. So if we look back here, 1 has a connection with 2, 4, and 5. So then in the network structure, we see a link going from 1 to 2, 4, and 5, and so on. And then we can go even further and represent this network structure as a matrix, which will be our weights matrix. So the weights matrix can be very large. It is of the square dimension of your observations. So if you have n observations, your weight matrix is n by n. For every observation, all the other observations are potential neighbors. And so if they are neighbors, the value is non-zero. And I keep it very generic for now. I don't say 1. I'll say 1 later. Right now, it's non-zero. It could be a cost. It could be inverse distance. It could be a number of things, right?
Could it be negative?
No, not negative. Positive. See? Positive matrix. Has to be positive. So it's non-zero for neighbors, 0 for non-neighbors. The other thing which may not be familiar, in network analysis, often you can be a neighbor of yourself. Here you can't. I mean, you can, but it complicates life. And let me just give you a short story as where it complicates life. In a lot of the statistics that we'll deal with later, we will use something called a trace of a matrix. And a trace is the sum of the diagonal elements. Okay? So if you have a matrix with zeros on the diagonal, you always know what the sum of the diagonal elements is. It's 0, right? If you have a matrix with ones on the diagonal, then you also know what the sum of the diagonals is. It's n. But one of the problems is that n can become infinitely large, and it becomes very hard to deal with. So it's always, in statistics, one of the golden rules, and if you do mathematical statistics, you will see this in the fine print, is to keep things constrained or constant. Okay? So setting the diagonals to 0 keeps things constrained and constant and easier to deal with. It's also an easier interpretation in that you have a notion of the neighbors, and you will take the average values of the neighbors. You don't want the value at the location itself mixed in with this. So no self-similarity. This is a matrix. We'll see concrete versions in a second. So every pair is in there. Every I as a row, j as the column. So we have different kinds of weights matrices. The easiest ones to use, and the ones we'll be using in the lab, are based on common borders, distance, right? So contiguity is a term that means having a border in common. So if I and j share a border in common, we have a weight equal 1. If they don't, 0. If we use 0, 1, we call them binary weights, right? So this is the weights matrix that corresponds to our example. And if we take a look at this more carefully, first row gives the neighbor structure for observation number 1. So we see that number 1 has a neighbor at 2, 4, and 5. If you look at the row elements, you get the 1 in location 2, 4, and 5. Right? So the zeros are for 2, are for 1 itself, then for 3 and for 6. 3 and 6 are removed from 1, so they're not neighbors. Right? So that's it. Right? You have the neighbor structure. You figure it out. A GIS can do that for you. But there is a quirk. Even on a grid, you can have different definitions. So the one that we just used is sharing a common border, right? That's in technical literature, sharing an edge, that's called a Rook criterion. And it's Rook from the chess, from the moves you can do in the chess. Right? Now, if you say, a neighbor, I don't care about these edges. I care about the corners. Do they touch corners? Then it's a Bishop criterion. It's not used that much. But the combination of the two, you say, well, I really don't care. Edges or corners, all of them, right? That's called a Queen criterion. Okay. So the most often used criterions are Rook and Queen. What's the difference between them? Big difference. Look how many there are relative to this case. There's 4 neighbors. The Queen case, there's double. Right? So this will matter when we do analysis, especially on grid and grid-like setups. However, in practice, a lot of the aerial units we work with are not grids. And then it turns out there isn't a big difference between Queen and Rook. But if you use grid-like systems, like in urban areas, or some states, like Kansas, have very gritty-like counties, a lot of four-corner situations, then there will be a difference. And this matters, as I said, the spatial autocorrelation is the combination of the weights with some multipliers. So if you have more weights, it's going to affect what your multiplier is. This just to illustrate the difference, and we'll be doing this in GeoDa. So this is just a random county in the Bay Area near San Francisco. The little tip is San Francisco. So you see the difference between the Rook and the Queen. I had to look long and hard to find an example where it actually mattered, but this is one, right? I have an old one that I've been using for 15 years, but I didn't want to use that one anymore. So, okay, that's the boundaries, pure boundaries. The GIS can figure this out for you or GeoDa can figure this out for you Then what do you do when you have points? Remember we said we can have discrete spatial units. They can be represented as points. Say the county seat as representing the county. So then we take the distance between the points. And since every polygon can have a central point or a centroid, which is the technical differences between the two, you can convert any polygon to a set of points and then compute the distances between them. So distance-based weights can be any function of distance that implies distance decay. So not distance itself. Every once in a while I run into a case where somebody uses distance in the weights matrix. That's a no-no, because we have to have less correlation as the distance increases. If you have the distance itself in the weights, we'll have more correlation as the distance increases. That runs counter to Tobler's law, so we better not mess with that. But in practice, more often, we don't actually use the distance itself because that creates scale problems. Think about it. We're going to use inverse distance, 1 over distance. That's intuitive. Distance decay, the larger the distance, the smaller this number will be, right? Now, we have data that are projected. I know you don't want to talk about this, but the projection is in feet. So now we have the distance between two counties in feet. That's not going to be a small number. So even if two counties are very close to each other, they may be, you know, tens of thousands of feet apart. And so 1 over tens of thousands is a very, very small number. It's basically 0 for all practical purposes. If instead we define the original coordinates so that the distance is in miles or in hundreds of miles, we'll have a very small number. Okay, so you have to be careful when you do, even though intuitively, and a lot of us, especially, you know, if you come from backgrounds like, you know, economics or statistics, we just love inverse distance. It makes sense, right? Well, sure it does, conceptually. In practice, you have to be very careful that you don't, by accident, create a zero weights matrix because of the scale at which your data are measured. So keep that in mind. So we have this notion of a distance band weight. It is what it says it is. If the two observations, I and j, are less than a critical distance from each other, we call them neighbors. If not, they're not neighbors. There's a problem with this. When we just arbitrarily come up with a cutoff distance, this works well if the areal units are all pretty much the same size. It doesn't work well if they have very different sizes. For example, if you're familiar with the geography of U.S. counties, the counties west of the Mississippi are larger and sometimes much larger than the counties east of the Mississippi, right? So if you want to make sure that every county has at least one neighbor, you need to pick a distance that makes sure that the counties that are furthest apart, in other words, the largest, are included. So the distance that we come up with for the US, I believe, is somewhere around 90 miles. Now, 90 miles is a huge distance for some of these smaller counties in New England, right? So this will have repercussions, and we'll talk about that in a few minutes, in that some observations will have very few neighbors, maybe even one, and others will have very many neighbors, which is not good for our analysis. That's a big practical problem. And if we take the distance and it's not large enough, then some observations will not have any neighbors. So this is an example of a distance band weight. I used 90 miles, and then I also had to look long and hard. Elko County, Nevada. Anybody been there or from there? I happened to drive through there last summer. So, but Elko County is one of these big counties, right? So if you take 80 miles there's no neighbors. It becomes an isolate. If you take 90 miles, it has one neighbor, just enough, right? Because it's the distance between the centers of the counties that counts. So this is something to keep in mind. Let me go back for a second. What do you do when this happens? Well, two things. Remember, we're interested in spatial interaction, spatial analysis. If they're isolates, they don't interact. They don't play. So for all practical purposes, they become missing values for your analysis. However, if you do standard analysis, if you do a regular regression, there's no effect. They just, you should include them because they're more information. What do you do when you have missing values in spatial analysis? It's very complicated. Of course, you can impute them, but by imputing, you tend to put in spatial autocorrelation structure. If your whole purpose is to discover that structure, you're kind of in a catch-22. Right? And that's why GeoDa really doesn't like missing values. We reluctantly are bringing them in the next version, but it's something that you really should be very wary of. Another way of dealing with distance weights when they're isolates is to take the k nearest neighbors. What that does is it takes the 4, 5, 6 nearest neighbors irrespective of the distance. So they could be very close, or those quote-unquote nearest neighbors could actually be pretty far. So it's a warping of the distance decay effect. It says, for all practical purposes, I don't care how far they are. What I care about is that they are the first that I encounter. Like in, there's some notion of intervening opportunities in when you look at interaction. When you go to the store, you consider the first 2 closest stores. And you don't care how far they are because you have to go to the store anyway. So if you live in Wyoming, you drive 100 miles. If you live in Chicago, you go around the block, right? But that's the same nearest neighbor. So there's a warping of the distance decay effect that goes on. Does that make sense or not? Depends on what you're studying. There's no hard and fast answer. A practical issue with k nearest neighbors is, what do you do when they're the same distance apart? So let's say you order the neighbors, 2 miles, 5 miles, 6, 6, 6, 6, right? 4 nearest neighbors, you have 4 at distance 6 to choose from to complement the 2 that you already have. Which ones are you going to choose, right? That's a problem. You either say, well, I'm not going to choose any, I'll take them all, but then it's not k anymore, right? Then it's not 4 anymore, it will be 6. Or you say, well, I'm randomly picking 2 from these 4, and then I stick with my k, and that's exactly what GeoDa does. Okay, an example of k nearest neighbors. So there's many weights. We'll talk about that in the lab. I want to talk about transformations of the weights and then the characteristics of the weights. So transformations. We typically, in our statistical operations, do not like to use the weights as 0, 1. There's only a few instances where we like to keep them that way as Boolean weights, as they're, or binary weights, as they're called. Think about if we're trying to summarize what's happening in the neighboring locations, we have our weights matrix. We can do kind of a weighted average of the neighbors, where the weights in the weighted average are the spatial weights, right? So if these spatial weights are 0, 1, what are we actually doing? We're just adding up the values in the neighbors. So we can end up with something that has a very different magnitude from the original. I mean, think of an example, house prices, right? Let's say we have a house, let's say just 100,000, right? It has 4 neighbors, let's say they're all also 100,000, right? So we have kind of ideal spatial autocorrelation. They're all the same, right? Now, if you take the weights as 0, 1, these neighbors will become 400,000. And so then you have to figure out, how can I make sure that this 100 and 400,000 are interpreted as being very similar, where in fact numerically they're not, but in fact, on the ground, they are. They're all the same, right? So to fix that problem, in some instances it's not a problem, most instances it is a problem. To fix that, we standardize the weights. We row standardize them such that the weights in a given row of the matrix sum to 1. What does that mean? In essence, you take how many neighbors you have and divide 1 by the number of neighbors. So if you have 4 neighbors, each weight is 1/4. It's 0.25. So then, going back to our example, we have 100,000. We have 4 neighbors at 100,000. We average them, and we come up with 100,000 again. And then we have perfect similarity, and we actually don't bring in any artifacts. This notion of the average of the neighbors is called a spatially lagged variable or a spatial lag. And we'll come back to that. I think we'll come back to it later. We definitely come back to it in the regression analysis, but only partially here. So then that's what our original weights matrix ends up looking like. You know, instead of 1, 1, 1, it's 1/3. But notice that in the third row it's 1/2, and in the fifth row it's 1/4. So this is no longer symmetric. So once you row standardize your weights matrix, the quote-unquote strength of interaction a priori between I and J is not the same as the strength between J and I, right? And this is a weird thing. And there's ways to deal with this, but it's something you have to keep in mind. You gain something, you row standardize, it becomes a nice average, it makes sense. You lose the symmetry, right? Another standardization that is actually not used very often, but every once in a while, and it's used more in the Bayesian literature, is a double standardization. In other words, your matrix becomes what is called stochastic. Why is the term stochastic used? The values are between 0 and 1, and they sum to 1, just like probabilities. So probabilities have to be between 0 and 1, and all the possible cases with all their probabilities have to add up to 1. So you do a double standardization. You divide each element in the original matrix by the total number of elements in the matrix that are non-zero. So the double sum over I and j of wij. And so then they're rescaled, and they all sum to 1. So then it looks like this. There are 16 non-zero elements in that matrix. You can count them. So every weight is now 1/16. So we have a rescaling. We keep the symmetry, but we don't necessarily have we have the same problem as before again. Because in the first row, we multiply 3 neighbors by 1/16. But in the, which one is it? The third row, we only multiply 2 neighbors by 1/16. So again, we have our scale issue and a difficulty of comparing this. So then another important notion is the notion of higher order contiguity. So neighbors of neighbors. So in time series, you have time t, say this year, and then last year t minus 1 is well defined. T minus 2 is 1 year before last year, right? In space, it's not that simple because we can go in 2 dimensions. So in time, it's very clear that 1 previous, so 2 previous is 1 previous, the one that's 1 previous, right? In space, first order neighbor is my direct neighbor. Second order neighbor is the neighbor of my neighbor, right? But I am the neighbor of my neighbor. So I am my own second order neighbor, right? And that's no good. That doesn't work. So we have to put in some constraint as to what these higher order neighbors can be, right? And basically, what we're going to do is to exclude anybody from double dipping, okay? If you're a first order neighbor, you cannot also be a second order neighbor. So a higher order neighbor is a neighbor of a lower order neighbor, but not already a lower order neighbor. Okay. Sounds very logical. It's actually pretty hard to do efficiently computationally, but it can be done. So second order neighbor, 4 and 3, 5 is in the middle, right? And you can do this in the network structure. You can think of this as taking 2 steps in the network structure. So you go from 4 to 3 via 5, right? So there's an extra step. So if we generalize this, of course, we have this redundancy. So we have, what are the second neighbors of 1? It's all the cells that are 2 steps from 1, which, as I mentioned already, includes 1 itself and includes all these other first order neighbors. So we have to remove them. So then higher order spatial weights, it's a recursive definition, meaning it goes back on itself. So it's kind of, that's a computational trick. It's kind of moving back. It's very appropriate for very complex problems in that you reduce the problem to solving the previous problem and then you kind of roll back. So order neighbor of order k is first order neighbor of a neighbor of order k minus 1, 1 less, but not already a lower order neighbor, so no duplication, right? But then if we define this, and we'll see in a second what it looks like, we kind of have 2 ways of thinking about this, okay? The way on the left is the Solano County again. That's the strict definition of the neighbors of my neighbor, my first order neighbors, that without double counting, right? So you see this kind of whole thing. So as such, this may not make a lot of sense. I mean, it does make sense if you're interested in finding out, in a fairly technical way. There's something called the spatial correlogram that computes spatial autocorrelation for different orders of contiguity. It's kind of the similar notion to what you have in time series when you look at the correlations between 1 lag apart, 2 lags apart, 3 lags apart, that kind of structure. But other than this very technical context, this isn't very intuitive. So instead, very often in practice, we think of higher order neighbors as kind of a counterpart of expanding distance bands, right? So you start with the ring of first order neighbors, then you add another ring of the second order neighbors, and so you keep including the first order neighbors. You're just growing out. And this makes sense if you're, remember, it's all about figuring out what is the critical distance, right? And we don't know ahead of time whether this is a process limited to the immediate neighbors or actually goes further. So we can, if we underbound the process, if the immediate neighbors are actually too few to model the process, we may build this inclusive cumulative measure. And finally, the properties of the weights. We can look at it visually like we just did. That's called the connectivity histogram map. But we are interested in the distribution of, the technical term is neighbor cardinality. Cardinality means how many there are, right? So we're interested in the distribution of how many neighbors there are in the data set. Ideally, we want not a lot of variability, right? We want, like on a regular grid, except for the corners, they all have the same number of neighbors. That's, in statistics, you like that. Now, in practice, if we deal with actual geography, there will be different numbers of neighbors. In the US, the counties have on average between 5 and 6 neighbors. But some counties have 20 neighbors, and some counties only have 1 neighbor, right? So how is that distribution, and at what point do we kind of have to go back to the drawing board and rethink our weights because they build artifacts in the analysis, right? And so the connectivity histogram gives you a formal measure of this. It gives you a distribution of how many spatial units have no neighbor. We call them isolates. One neighbor, two, and so on. We want that distribution to be nice and symmetric. So the things we watch for is obviously isolates, right? Islands. Islands do not play in spatial analysis. So if you're interested in spatial interaction, they just don't count, right? If you're interested in non-spatial analysis, fine, not a problem, right? Also, what you don't want is a very large number of neighbors, because there's too much averaging going on. It's too much smoothing. When you smooth too much, you lose variability. In statistics, everything is about variability. Everything, if things don't change, go home. There's nothing you can do. You want variability, and you want to mesh this variability. So if you smooth too much, there's not enough variability. What you also don't want is a bimodal distribution. Like some spatial units have very few neighbors, and some have very many neighbors. And there's one particular example in the US, and it's the state of Virginia. Anybody from Virginia here? Do you know what's going on in your state with the counties?
With like the distribution of wealth and ideology?
No. It's just the size of the counties. Some counties are city counties. Some counties are county counties. So the city county is inside a county, right? So they have one neighbor. So if you look at the distribution, there's a mode at 1 for all the city counties, and then there's a distribution for the others. That's not a good thing, okay? Because we're averaging the neighbors. If you only have one neighbor, there's no average going on. So too much averaging is not good. Too little averaging is also not good, right? So this is what you like to see. This is the example for the US, comparing Rook and Queen contiguity. And as you can see, they're very similar. There's only a few differences between them. And we'll do this in the lab in GeoDa. This is a distance-based distribution for the US counties. So you see, this is a mess, right? Some counties have very few neighbors. Some counties have lots and lots of neighbors. Obviously, given the same criterion for distance, the large counties will have very few neighbors. The small counties will have many neighbors, right? Same thing happens when you look at census tracts in a city. Typically, the census tracts in the core of the city will be small. As you move out in the suburbs, they get larger and larger. Classic example, and be very careful if you ever analyze Miami census tracts. If you've heard of the Everglades, Everglades are a census tract. It's huge. So it dominates all of Miami. So you have to really take that out or do something with it if you're going to do a spatial analysis, because it will drive the distance between the Everglade tract, or there's like 3 or 4 of them, distance between that tract and its neighbor will be so large that all the other tracts in the city will be neighbors of everybody else. And that's not what you want. You want distance decay. You do not want that everybody is correlated with everybody else equally strong. That is a non-information situation. So then the last slide I want to show you is this one. This is the contiguity histogram for k-nearest neighbors. K is k, right? They all have k neighbors. That's it. So this is a single bar for k, and that's it. Okay? So in the lab, we're actually going to do this. Okay, that's it.